Hello Chem 1B. This is chapter 16, lecture video 8, and we're going to be covering salts, really. Ionic compounds can actually be either acidic or basic, depending on what's the cation or the anion in the ionic solid. So we need to kind of do a little bit of background here. When a salt of a weak acid or base is added to water, it's going to dissociate completely, assuming it's soluble. So for instance, NH4Cl is a soluble ionic compound. And when it dissolves, it breaks up into NH4 plus and Cl minus. Now, NH4 plus is a weak acid. So this salt is going to give a solution with a pH that's acidic when we dissolve it in water. So how do we tell whether the cation is acidic or neutral, or is the anion basic or neutral? We have a bunch of rules for this. This reaction is going to go to completion, as you notice with the arrow here. This is not an equilibrium. But this guy's a weak acid, so it will go on to have an equilibrium reaction, as all weak acids do. Here's our weak acid dissociation. NH4 plus is reacting with water in the solution to form H3O plus and NH3. This has a Ka. And so problems like this are generally going to involve two steps. First, we dissociate the salt, like so. There's no equilibrium here. And then we do a equilibrium. It could be a Ka, it could be a Kb equilibrium, depending on what the salt is and whether or not it's going to make an acidic solution or a basic solution. So if a conjugate acid salt, meaning a salt that contains a weak acid, like NH4Cl, is dissolved in water, the pH is going to be greater, less than, or equal to 7. Well, it has an acid in it, right? So it's going to be less than 7. Because we're going to form H3O plus due to this equilibrium here. Now, if the salt contains a conjugate base or a weak base ion in the salt, well, then the pH is going to be greater than 7, and we're going to form OH minus in the equilibrium that's established after the ionic dissociation. So how do we tell if a salt has a weak acid or weak base in it? Well, there's some rules to that. Okay, so before we can talk about rules for ionic compounds, we have to talk about metal ions. One of the things that is kind of interesting is metal ions can act as acidic or basic, depending on what metal ion we have. I keep meaning to fix this slide here. Expect my metal ions to be neither acidic or basic. That's completely wrong. Most metal ions end up being acidic. This statement, though, is true for alkali and alkaline earth metals, with the exception of beryllium. So, for instance, sodium plus, lithium plus, potassium plus, Rb, calcium 2 plus, magnesium 2 plus, anything in the first two columns on the periodic table other than hydrogen and beryllium, if they're an ion, they are neutral. They do not actually change the pH of the solution. However, if we have any other metal ion present in our ionic compound other than one of the metal ions in the first two columns of the periodic table, then it's going to be an acidic metal ion, meaning it will act as an acid. Now, how does that happen? The way it happens is due to the fact that in reality, most cations or anions are hydrated when in an aqueous solution. In the case of metal ions, they're bound to about a group of about 6 water molecules. These coordinated water molecules can react with a regular water molecule to form H3O plus. So for instance, here's Al H2O6 3 plus, right? So we have one of these hydrogens here can actually jump ship. In our case, I circled the wrong one in this picture. This guy goes away, right? It attaches to H2O, forms H3O plus, and you can kind of see here now we have an OH group attached to our aluminum ion instead of H2O. We still have 5 other H2Os still attached in an octahedral structure, but this has a Ka of 1.4 times 10 to the negative 5. You can see that that's not actually that small of a Ka. It's, I mean, for Kas, that's a pretty reasonable Ka. So this is actually a relatively weak acid. In comparison to other weak acids, it's about the same strength. This is true for a lot of metal ions out there. So you should be aware of that which metal ions are neutral. The alkali metals and the alkaline earth metals, they are neutral. Every other metal ion out there is going to be acidic to some extent, with one other exception that you should know, and that's Ag+. This is a neutral metal ion, and you should be aware of that as well. But other than that, every metal ion on the periodic table other than those groups are acidic, and these ones are neutral. So let's talk about whether a salt is acidic, basic, or neutral. And what I mean by that is, if I dissolve this salt, this ionic compound in water, am I going to get an acidic solution, a basic solution, or a neutral solution? Well, we have some rules for that. It's all about the properties of the anion and the cation in the ionic compound. So amphoteric species that we talked about earlier in this chapter, they actually can act as either an acid or a base, and I'm not going to be putting them in ionic compounds that we deal with here. They're very difficult to predict whether they'll act as an acid or a base without a lot of information in addition. So other anions, this is what we're going to focus on first. With anions, they are neutral if they're the conjugate base of a strong acid. For instance, HCl is a strong acid. Its conjugate base, Cl-, is neutral. So if we have this anion present in our ionic compound, it's not going to affect pH. The cation might still, but the anion won't. All of the conjugate bases of our strong acids, with the exception of sulfuric acids, are neutral. So there are really only 5 neutral anions out there, and that's Cl-, NO3-, Br-, I-, and ClO4-. These are our 5 neutral anions. You need to memorize them. So, or just know that all the strong acids you memorized, if you have their anion present, except for sulfuric, it's a neutral anion. These guys will not affect pH in either direction. Otherwise, if it's an anion, and this is the other bit here, it's basic, right? So if it's not neutral, anions are basic as a general statement. So either it's neutral or basic, and these are the neutral ones: Cl-, NO3-, Br-, I-, and ClO4-. If it's not one of these guys, it's a basic anion. Simple as that. Now on the other side, the cation side, if we have a group 1 metal, alkali metal, or group 2 metal, alkaline earth metal, the cation is neutral. Pretty much everything else other than, also silver, Ag+, is another one. If it's one of those groups, it's neutral. If it's not, it's acidic. So that's kind of how we tell. Now, that creates a scenario where we have really 3 different things occurring, right? We could have a salt made up of a neutral cation and a neutral anion. In this scenario, our salt is going to be neutral, because neutral and neutral, nothing's affecting pH here. So NaCl, group 1 metal, conjugate of a strong acid, neutral. Same thing here, except group 2, group 1, strong acid conjugate. These guys are all neutral. We could have a salt formed from an acidic cation and a neutral anion. In this case, we're going to get an acidic salt, because the anions aren't affecting pH, but the cation is definitely going to be acidic, and therefore we get an acidic solution when we dissolve these guys in water. The third scenario is we have a neutral cation, right? But a basic anion. right? So in this case, right, Na, K, and Sr, these are all part of the neutral cation group. But F minus, acetate, and chlorite, they are all conjugates of weak acids, i.e. weak bases, and so we're going to get a basic solution here. The fourth scenario is by far the kind of hardest to lock down, and that is when we have one of each. All right, we have an acidic cation and a basic anion. This salt could either be basic or acidic depending on which one is stronger. You can kind of think of it as an arm wrestling competition. If the cation's a stronger acid than the anion is a base, then hey, it's going to be an acidic solution. Or vice versa, it'll be a basic solution. So it really just depends on which one's stronger. So let's look at an example of that, right? How do we figure out which one's stronger? Well, the way to do it is by looking at our Ka and our Kb and comparing them. The Ka for the cation, the Kb for the anion. So let's look at this salt, AlClO3, right? So in this salt, we have an acidic cation. Aluminum is not a group 1 or group 2 metal, and it's not Ag. And we have a basic anion. ClO minus is a weak base. So we got to figure out which one is stronger. And then compare the two, Ka, Kb, figure out which one's stronger. Whichever one's stronger, that'll tell us whether this is going to make an acidic solution or a basic solution if I add it to water. So the Ka for aluminum is 1.4 times 10 to the negative 5, right? And you're not going to find the Kb of ClO minus. What you can find, though, is the Ka for HClO. Now, that's not super helpful right now. We need the Kb of ClO minus, but how could I get that given I have the Ka? Well, this brings us back to Kw is equal to Ka times Kb. And we have the Ka, and we know Kw, so I can use this equation to solve for Kb. All right, I know Kb is going to be equal to Kw divided by Ka, or 1 times 10 to the negative 14 divided by 2.9 times 10 to the negative 8. If I do that division out, I get Kb is equal to 3.4 times 10 to the negative 7. I can then compare my Kb value to my Ka value and see which one's bigger. So in this case, we see that the Ka is the larger of the two. 1.4 times 10 to the negative 5 is larger than 3.4 times 10 to the negative 7. So our Ka is stronger. This means if I dissolve this salt in solution, we're going to get an acidic solution. Okay, so let's do another example problem. Given the following table, which solution will be acidic? So how do we figure this out? We gotta look at the Kb compared to the Ka for our anion to our cation, right? So let's look at our options here first. I know I can cross this guy out immediately. NaCl is a neutral salt, so it's not gonna make an acidic solution. The rest are harder to tell because cobalt is definitely going to be an acidic cation, right? This is acidic. This is basic. Same thing here. Acidic, basic, acidic, basic, and so on. So the rest of my four options here are composed of salts that contain both an acid and a base. In order to figure out whether it's an acidic solution or a basic solution, I need to compare the Ka for CO to the Kb of C2H3O2 for this salt, and similar for this one, but Ka of F to Kb of acetate, and then finally Ka of Fe to the Kb of BO3 3 minus. Well, I have a bunch of Ka values given to me in this table, right? Like I know all these Ka values. So these two I don't need to change at all. They're what I need for CO2 plus and cobalt 2 plus and iron 3 plus. I got those. We're good. Those are the Kas. They're acids, so we're okay. These two, if we look at them, they're the conjugate acid of the base that I need the Kb of. So I just need to recalculate these as Kb values, right? So the Kb values of CH3COOH, or sorry, COO minus, and BO3 3 minus, I need these two values. And we can get them using our expression that we did on the last slide, right? Kw is equal to Ka times Kb. So if we do that really quickly and just solve, we get 5.6 times 10 to the negative 10 here for that Kb, and we get 5.6 times 10 to the negative 2 as our Kb here. So now we need to compare these. Well, if we look at BO3 minus, this guy here, it's bigger than both of our two acids, cations. So it can't be present if we want the system to have a basic solution, or I'm sorry, acidic solution, right? So these two are scrapped then. They're both not the correct answer because both of them are going to be basic salts, meaning they'd make a basic solution. Really now it's down between these two, and we have to look at, okay, this guy compared to these two. Which one is going to give me a acidic solution? Well, if we compare the Kb here to the Ka here for cobalt, you notice that Kb is larger than Ka, so it can't be A. That's a basic salt, just barely, but it is. The only one that's stronger is irons. Irons, the stronger value over 5.6 times 10 to the negative 10. So our correct answer here is going to be B. And hopefully that helps. All right, so let's do one last problem. So what is the pH of a 0.35 molar solution of calcium cyanide? So this is where we're calculating the pH of either an acidic or basic salt. In this case, we actually have a basic salt. Now the first step is writing the formula of calcium cyanide, CaCN2. This is something from Chem 1A that you should have learned how to do. Now, I know this guy dissociates 100% into Ca2 plus aqueous plus Cn minus aqueous. Now the bit here is important, is this is going to have a 2 here. This 2 affects the problem because I know if 0.35 molar of this was dissolved, then I form 0.35 molar of this, but 0.35 molar times 2 of cyanide, which is the part I care about. This is a neutral salt, or a neutral cation, so I don't care about it. So the next bit is that Cn minus is a weak base. It reacts with water to form OH minus and Cn, HCN. This is aqueous, pure liquid, aqueous. Now, this is our concentration of Cn minus in solution. So if we write out our ice table, we have 0.70 molar. Don't care about pure water. It's a pure liquid. And 0 of these two initially are products. Our change is minus x, plus x, plus x, x, 0.7 minus x. And the next bit is kind of tricky. This is not the equilibrium constant we need because that's the Ka of HCN, and HCN isn't what's initially present, it's Cn minus. We can't use this Ka value. We have to get the Kb value. we can do that using Kw is equal to Ka times Kb, right? So Kb is equal to Kw over Ka, or in other words, 1 times 10 to the negative 14 all over 4.9 times 10 to the negative 10, which in this case is equal to 2.04 times 10 to the negative 4, I believe. Sorry, nope, 10 to the negative 5. Okay, at this point we can just say, hey, 2.04 times 10 to the negative 5 is equal to x squared all over 0.70 minus x. Again, I'm just getting this from our ICE table. I'm going to assume the 5% rule here, cross out minus x, and I can resolve this for x, right? X is going to be equal to 0.00378 molar. Again, this is equal to our concentration of OH minus because we had a weak base here. I can get the pH through POH, right? So the way I'm going to solve this is get the POH, which is just negative log of that value. That gets me 2.42. And then I know pH is equal to 14 minus 2.42, or 11.58. And this would be my answer. All right, so if you have any questions, just let me know, as always, in my discussion session or in my email. Have a good day.